Thank you all for coming. Similar to the previous talk, this is also focused on a real research, and it's related to using Java to predict future. It looks very promising. So it's something related to actually using an existing data set to form a mathematical model of a human brain and to try to predict something that didn't happen based on the previous, let's say, data set and previous patterns in the data. So since two students are here standing, back. Vjori Hoxha is here. He is one of the best students in his generation, and he is very talented developer, so we decided to include him to this research. I teach a course named Foundation Mobile Design, and we introduced React Native this year. And Vjori actually finishes all the in-class assignments within 15 minutes. So the class lasts for 75 minutes and he's done with 15. Come on, it's too easy for him, so he should be included in a research like this. And Ivor Baric is also very talented engineer, and once he had a homework related to InVision. You know how to use InVision? Okay, it's a prototype application to create, let's say, mock-ups of the screens to be able to simulate the real work of an application. And of course, the assignment was to create like a tip calculator for a waiter in a restaurant. Something, I would say, pretty straightforward. But his application was so real, I didn't know that it was an InVision application. He created like, how many, 400 mockups or something? Almost, yeah. So, and it was, you had all those combinations covered, and it was really astonishing. So I decided Ivor is our guy, so we need to do a work with him. He is also, believe it or not, the tallest student of his generation. So that's why, two main reasons to include him. Now you can actually show the next slide. So I'm Aleksander Radovan. I work as a Java team lead at ICD, and also work as a senior lecturer at several universities in Zagreb and around Zagreb. And of course, Vjori Hoxha is our student, and Ivor Baric, and they will mostly talk the tallest. That's very important, the tallest student, and they will talk about their experiences, and they will try to well, predict two events in the future. The first one is to predict a tsunami in the future. Luckily, we are away from the coast, so we are not in jeopardy. But for example, we got a nice data set related to French Polynesia. So we use this data set to actually simulate and try to, let's say, calculate when the next tsunami happens. And Ivor found a nice data set about the air pollution and air quality in Zagreb, and he is going to actually predict what happens in the future. So guys, the mic is yours. Please take the stage.
All right, thank you once more for joining us in this presentation, and let's begin with my section. So, all of this research, let's say, or experiment started with initial question that Professor Radovan, which I wanted to thank him and Professor Mihailovic for supporting us in this research. So he asked me, like, can there be a pattern between weather parameters, so historical weather parameters, and natural disasters? And we said, let's try it, let's give it a try. And then we researched about different natural disasters actually, and we found out that tsunamis are not worked as much with neural networks and programming in general. So, is there actually a pattern between weather parameters and tsunamis? Like, what do you guys think?
Yes.
No? Okay, let's find out together in the next slides. So, as we know, tsunamis are currently predicted using physical devices set up in the ocean in those countries that have mostly tsunamis. And then they report back different data into their country, their initial country, in order for them to, let's say, to predict if the tsunami is going to occur or not. But what they actually do is trying to measure the Earth movement below the sea level, and that's how they currently predict tsunamis. And according to world data, actually only 75% of tsunami alarms are fake, because it's one of the hardest natural disasters to predict and to work with that. And that's really intrigued me and Professor Radovan to go into tsunamis. And so we said that let's try to find data set historical weather parameters and to find a pattern between that and tsunami occurrence. Because we know that we know the dates in a specific area that tsunamis occurred from the historical perspective, and let's try to find a pattern between those historical weather parameters that we think and that they correlate to tsunami occurrences. So for this purpose, we use Java programming languages and Encog framework. Encog framework is a neural network framework used and written in Java in 2008, and it's currently also a project being developed. And Encog tries to simulate most of the learning techniques that are mostly known in today's neural network learning. So the data set for this particular learning is composed of the date, of course, from the month, year. So this will be our input, which consists from the last 10 years. 2018 is not included since we started this research in 2018, and we include only 2008 up to 2017. And we take the global summary of the month, which is the average of 5 weather parameters, historically speaking, for average temperature, sea level pressure anomalies, wind index, outgoing long-range Earth radiation index, and dew point. As also to mention is that it's really hard to find a good data set regarding the input data set which correlates to tsunami prediction. So we try to take only these inputs and weather parameters, and the ideal output is composed of 2 known tsunamis that occurred in this specific location. As Professor Radovan mentioned, we worked with French Polynesia, which on February 2010 and March 2011, 2 definite tsunamis, so 2 definite tsunamis occurred there. So for this purpose, we used supervised learning, since we know, since we have an input data set, and we know when the tsunamis occur. So the purpose is to try to find a pattern between those weather parameters and mark them and try to see the actual output and compare them to the ideal output, which will be when those definite tsunamis occur. First, the data needs to be normalized, so we normalized the data from a range from 0 to 1, so we can take from a percentile output. It's not on mine.
What's wrong, guys? He was on the wrong side. He was on my structure. There we go. There we go.
Nice. Okay.
Looks the same. Looks the same.
only the hidden layers are different. Okay, so for this, the input data set is normalized from a range from 0 to 1 because we want in the end to get percentile probability output of the actual output, of the ideal output that we know for that particular day that tsunamis occurred. And for that, Encog has, we use the resilient propagation technique that Encog has, which tries to simulate the heuristic learning from the actual learning, which means even though it's not a perfect prediction, but it still is sufficient for our case. So after normalizing the input data set, the neural network is composed of the input layer, which takes one neuron per each input attribute, and the biased neuron, which is colored with color red. Also, there are two hidden layers, each of 20 neurons, and one biased neuron, which is colored with red. And these hidden layers take the activation sigma ID function, which tries to give an output of a positive number, since we want percentage prediction between those weather parameters and the actual output, and that's why activation sigma ID function is used. And the output layer, which is the actual output. So the testing part. First, I went with 20 rows with 7 columns, and tried to increase the rows by each testing phase. First, with 20 rows, and in a set to a margin of 0.01% error rate, the actual output was much lower than we wanted it to be. So the testing went, so the training part actually, and the testing went from 20 rows and gradually increasing the input data set from 20 rows, and each time we test the model, each time increased by 20 rows. So in the end, we got into 120 rows, which is 10 years of weather data set. That's with what we were limited because we couldn't find much more, unfortunately, data set. And this is the final testing, which ran about 600 epochs or learning iteration, and we can see that the error rate starts at 50% and it decreases up to a really small error rate. And the testing results were great from our side, which we can see that. So these are only few let's say outputs, a few rows, because the picture cannot fit them, but we see that from other months and previous years, we have an actual prediction from the neural networks, which is a really low margin error number, and the ideal, which is our ideal output, with labeled with 0. And here is the February in French Polynesia, that we knew that tsunami occurred there, and the neural network predicted it with 90% that it was, so there was a correlation between all these weather parameters taken from previous years, and yeah, it pointed out 99%. And also for the March 2011 tsunami, the neural network's actual output was 71%, and the ideal one, which was 100%, and it was a really good result also for that. And you can also find the news coverage, which this picture was taken from ABC Australia, which reported in 2010 February that the tsunami hits French Polynesia, and we can compare it to the neural network actual output. I know this not perfect because the data set is limited, and we are only working with 10 years of data set. The more data set it would be great, but we can conclude that natural disasters can be predicted if we use this training method, and if we try to feed it with forecasting weather parameters in the future. So this will be our future work, trying to get the neural network safe, the training procedure, and then to feed the neural network with forecasting weather parameters, and try to see if the final prediction will be sufficient for us. So that was all from my part. Thank you, and I'm going to leave the stage to my colleague Ivor for the second session of this presentation.
Hello. They passed me the mic like I'm a rapper. I feel like a rapper. All right, so how many people here know what AQI is? No? No? Oh, you? Thank you. Air Quality Index. An applause. First of all, I'm going to follow my colleagues' examples, and I want to thank you to Professor Radovan and Professor Branko for helping us out with these projects. And I'm going to continue with saying that Air Quality Index is something that is not standardized, and that is a problem in today's world. But you know, we're not here to talk about weather parameters and blah, 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 right? But we had to pick a formula by which we're going to calculate the air quality index based on the parameters that are being predicted, right? Because first of all, we started with predicting the air quality index, but then we finished and we were like, you know, we have a triangle that we have the two sides, right? And we have the values of those sides, and we're trying to predict the third side. Why? You know, why? We have the formula for that, right? We need to predict those two sides and then calculate the third side, right? So we are predicting the parameters for the air quality index, and the air quality index itself is being calculated afterwards, right? And we're using the EPA Victoria, so that's Environmental Protection Agency Victoria formula for predicting those, and that's like chemistry, but we're not going to get into that, sorry. All right, so yeah, the purpose, like I just said, is predicting those parameters, and we can get into them. I will talk about the data set. Yeah, as when I started doing this, Professor Radovan told me, you know, listen, 90% of this is just getting the data set to work, and like 10% is just setting up, you know, playing with the neural network, right? And that is exactly what happened. Getting the data set, a good data set, is exactly what was necessary, right? So I'm not going to focus on talking about, you know, resilient propagation, because my colleague already covered that with the layers and everything, so I'm going to focus mostly on the data set that I needed. So, firstly, so this is a part, it's probably bad quality. This is a part of the Excel sheet that I extracted the data from using Java, of course. That's how the data looked like. So that's our ideal. I had 2,872 days, going back from somewhere like 21st of January 2011 till January 2019, right? And I took all that data from HALP, Hrvatska agencija za okoliš I something like that. I don't know, right? HALP, I don't know HALP, right? So I took that data, and first thing I realized is, like, you know, every third row has a blank in it. What am I going to do with blanks? So I actually ended up ignoring 1,066 rows because of blanks. So we ended up with the rest, and these are our parameters. So we have days that go from 0 to 364. We completely disregarded the prestupna godina, I don't know how you say it, the leap year, right? Yeah, prestupna godina, so the 29th of February 2012, 2016, I just ignored those, right? Because 364, so our parameters are based on dates too, so date had to be included. I firstly tried without the date, and the predictions that I got were terrible. Because air quality mostly depends on the time of the year. In spring and summer, when, you know, everything is blossoming, blah, 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 you know, it's really low. Like, all the parameters get low. While in the winter and the fall, those parameters skyrocket. So it's like a sigmoid function. That's exactly why I used activation sigmoid for all of my layers. It's like a sinusoid, you know, it goes like this. And I was actually playing with that in order not to waste time on choosing the activation function. So we have O3, ozone, right? Goes from 2 to 432. We have the CO goes from 0 to 3 and all that, you can see that. And actually the worst part for Zagreb, believe it or not, I don't know if you have allergies, is PM10. That's particle matter. So it's like, you know, allergy people, how do you call it? Yeah. Pollen, right? So it's the one, according to EPA Victoria, that made our air quality in a few cases throughout those years really bad. Now, my neural network structure, so I have also two history. First has 48 neurons, second has 24, so it's kind of like a digression, right? And of course, like we've explained, so you have the biased neuron on each of those, right? And the input parameter, which is really important, we actually decided to take 4 days as the input. So I have 24 parameters in the input. So I take, each day has 6 times 4 is 24, right? So I take 4 days and I'm trying to predict the 5th. And I'm just shifting down. And that's how it works. And here, by the way, I don't know if you noticed, these days do not go by 5. And these are like my first 5 ideals. And that's because of the blanks. Because, you know, I had to skip the blanks. And that is also a big reason why this neural network isn't working as I wanted it to work, but it's pretty fair. So, let's continue. Here we go. I have 10 more times like the training epochs and my colleague did. And the reason why the error had to be so low, I'm not overtraining my neural network, is because I did the normalization of the data myself, because I wanted to denormalize it myself, not use the Encog methods for denormalization because they give you some weird results. First of all, when you normalize it, Encog takes values from 0 to 1, and when I did my normalization, I gave it values from 0 to 1. And I knew what I did, so it would be easier for me to, when I predict the values, get them back to what they really are, right? So this is an example of my output, all right? So it predicts pretty well, and it gives you, so this is the 5th day, the ideal 5th day would be this, and the output 5th day is this, right? And what I have to say about this is it's really good, and I like it really much, but just like with my colleague, we really, I don't know what happened. We really depend on the data. And that is a big issue, especially for, I don't know how it is a creation agency. Like, I'm not trying to bash anyone here, but having blanks, really? You know, I was going through that data, I was like, really? So one day you just decided not to measure SO2. Okay, I have to ignore the whole day. Yeah, but that's it. Hope you enjoyed the show. Q&A, anybody? And yeah, by the way, we have really good air quality. I forgot to say that. Appreciate the city you live in. And the answer, is it safe? No, it's not safe. Global change, global climate change is a real thing. We're going down, we're flunking, but we're not flunking as fast as other countries, all right? So, we're good. All right, any questions? No? All right, thank you.